Which admission are you talking about, Sydney? Is it a lab?
So this morning, when I was going over some code, because I always like to review it before I submit it again,
Right.
I copied the links and I pasted them in Blackboard. And I know that I've done this before. I can't remember which time. So I got to go back through it and confirm. Everything that I've done and submitted has been submitted. I'm just not certain if some things I might have submitted just through Blackboard. And I can't remember right now, but it just crossed my mind this morning. So I just something that I have to look into.
Okay. All right. I have, I think the project should be available now. Let me see. The project description. Yep, it is available in Blackboard. I want to talk a couple of things about this project. This project is, well, it is. I want it to be a little bit more difficult than the lab. But end of the day, it might take a little bit more time. You have 2 to 3 weeks, and also you will be writing something like a C++ library. So that's the idea. All the no, project is not a good trip for final. Project is it gives you 20 points. That is something. So whereas unlike previous times, this time I split the marks into, let's see, usually final carries a lot of weight, like 40%. This time final is just 20%, whereas project is 20%. So that's where the rest of the marks go. So it is important that you do a good job with the project. We will spend some time, unlike homework, where we just grade a randomly selected question. Project, we will look at everything. So what this project is, it is intended to be like developing a C++ library for matrix operations. Like you will, like how you will use a math library similar to that. So you will have to show addition, subtraction. Those are two very easy things. And then multiplication, I'm sure I heard that many of you have done that in the other course as well. And the matrix solving, that will take some time. And then inverse. So matrix solving is Gaussian elimination. Inverse is LU decomposition. So let me see the project, what is asking. Yeah. So read all the introduction, details, and let me know. And also, okay, the one thing I want to ask is, we have come across some issues where there was hard to tell, difficult cases, honestly, of similarities in codes. It is hard to detect. It's a difficult problem for everyone. So that's why for this project, I asked that it is said in the project description that please work on triplet. So at least we can see. Again, I know it is possible still, but if you can, I mean, that is stated in because we want to see the history of your work, and we don't want just the code to just appear. Replit is a very user-friendly thing. That's where you have been submitting. All I ask is, do your work there so that we can see progress rather than just a whole project appearing. I'm sure there are explanations for that. Like you might have worked from a Visual C++ or something. This time I asked that for the project, please do work on the Replit. It is not very hard. I mean, you know that. You're all familiar with that. And it is kind of a growing platform. A lot of people are using it. The good thing for us creators is that it gives us an opportunity to see progress. And even if there are similarities in code, we can just see that, okay, look at this is how it is progressing, so it don't make sense. Okay, so we're almost nearing the end of this course. So today's lecture 15, and then 2 more lectures. I plan to record those 2 and upload there. And that way we can start reviewing. So after I finish lecture 17, I'm going to go back and review. Uh, so how I'm going to do the review is I'm not going to review the lecture notes, but I'm just going to do the homework in class. So while I'm doing the homework, I will do some review if necessary as well on theory. So I plan to do all the homework in class because we have a couple of classes, I believe 3 or 4. So I think I should be able to do all the homework, but I'm not sure. So if you have any preferences, oh, can you please do this homework? Send me the list. I will also prioritize based on that. What else? So yeah, there are some remaining homeworks I need to upload, which I will do in this week. Everything will be due before December 1st, so that you don't need to worry about, as you go towards the final, I know you will have so many other things. At least I am ahead in that regards. A lot of things, I'm taking the lecture early. Yeah, there will be 2 more homework sets. Project, yeah. All right. All right. So once again, this lecture is a very short lecture. Numerical, that is true for all the remaining lectures. They are short and kind of straightforward. Um, Nothing to remember. A lot of formulas, that is for sure. If you just open the lecture notes, it might look a little bit overwhelming, or so many equations. That's why I'm here to simplify that. I will tell what each of these are, so that if you just listen to the lecture, that will save you a lot of time trying to read this by yourself. So let about numerical differentiation. Review lecture 4. In lecture 4, Taylor series, if you just go back to lecture 4, no, there's no group project. Did I say the project is submitted by group? I cannot change that. Yeah, the project is not group. I want you to work individually because it's not very hard. It's very similar to a lab. Yeah, I don't know if I said that somewhere before, but I take that back. You have to, you have to say it. It doesn't say anywhere in the project that it is group work. Okay, if it is set in the syllabus, I will change that. But yeah, project is probably I said that. That's how I remember it. But I will say this again and again, that project is not a group work. Please work individually because it is not very hard. There's nothing actually for group member to. It is not a huge project as I would have wanted it to be. Okay, what I was saying. Okay, review lecture 4, where you will see at the end of lecture 4. At the end of lecture 4, you will see some discussion about numerical differentiation. So what is numerical differentiation? In lecture 4, we were using Taylor series. It was taught as an application of Taylor series. And that's this whole lecture, it relies on Taylor series to derive all these numerical differentiation formulas. So what is first of all, what is differentiation? What is differentiation? So if you have a function, so fx, you know what is differentiation, but let's review it. So fx and then x, so any given point here, let's say xi, so we call it dfx by dx. dfx by dx is something we call f prime x. That's a gradient at x. So it is a gradient at x. So if this is f prime xi, which is the point I showed you, that's gradient at xi. So that is xi. So what is gradient? So that is, this is horizontal. If I draw a horizontal line and then the tangent at that point, if this is theta exactly at xi, then fxi is tan theta. As you can see, based on what point I select, right? If I select xi to be here, the gradient is this. If I select xi to be here, the gradient is, every point is different. So it depends on, if since it is numerical method, we want to compute it using some data point. Now there are two ways to find the differentiation. If it is an easy function, like if fx is 3x cubed plus 4x, that's very easy to find differentiation. F prime x is 9x squared plus 4. Any xi is equal to 2, we can find the gradient by substituting x is equal to 2. Any xi you can find. But problem is, there are many cases where, where numerical differentiation, sometimes the function is, if the function is not defined, that is, we only have some data points. So we have some data points. So like we will have some data points like x, fx, supposed to be a function. We have some xf, xi pairs. So that could be a function like this or this, we don't know. Yeah, there are many approaches, many intuitive approaches. If we have some data points, previously we saw that we will just make this into a function and then solve it. That is what we were doing even during integration, numerical integration, and to some extent interpolation. So it's the same thing. So what we are going to do, given data point, we will just try to build a function and then find the derivative by taking the derivative of that function. But what these approaches, three different approaches. One is forward difference method, Newton's forward difference method, Newton's backward difference method, and Newton's central difference method. And then we'll also see taking the derivative for unevenly sampled data. For that, the intuitive approach is very similar to this. We will just fit a function and then take the derivative of that function, whereas these forward, backward, and central different approaches, they are very good if the data is equally spaced. For example, you have some data points x1, x2, x3. The difference between each x data is, if it is the same, if it is age always, then this Newton approaches will work. If the data, in some practical cases, we don't have data like that, then we study an approach for that. So that's the summary of what is going to come. The good thing about this, now I'm going to introduce these forward and backward and central different approaches. We already studied briefly about these approaches in lecture 4. So that's, I don't know if you had a chance to review it, but we will review it now anyway. So let's start. So we're going to do the first derivative of forward difference method. So it start with the Taylor series expansion. So first of all, let's some notations here. So since I already said that this difference here is always equal, so if I have x here and then x plus h is the next point and the forward direction, x minus h is the next point in the backward direction. Obviously the next point we have is x plus 2h, x plus 2h, and then on this direction we will have x minus 2h, and so on. So that's where we have we have x, we have fx, we have x plus h, we have fx plus h, we have x minus h, fx minus h, and so on. So we assume this data is available. So we have some data points, and our goal is to estimate the derivative. So can someone, to anyone, remember what is the formula for, if it is the forward difference method, what is the formula for derivative? What is an approximation of f prime x using the data given in this figure, at least intuitively? All right, so we will just do a tangent, yes, but I need a, based on the values you see here, x plus h, fx plus, based on that, can you give me a formula for derivative? So we're going to use the geometry. So let me take this triangle and put all those values here. So this triangle, I'm just enlarging it. This point is x, this is x plus h, and then this point, oops, so this point is fx, y, and this is fx plus h. So tan theta is the derivative, so which is this length divided by this length. So opposite length is f x plus h minus fx divided by x plus h minus x is h. That is the approximation for first derivative. So similarly, we can write the this is using geometric means, and then similarly here using the backward approach will be fx minus fx minus h or h, and then central approach is fx plus h minus fx minus h divided by 2h. No, there is no group. I mean, no group. So basically, one person. You have to do the project individually. It is not a difficult project. It is very similar to lab. Okay. So these formulas we studied, and I kind of reviewed it using geometry. Now we are going to do the same using Taylor-Swift's method. So look at equation 1. I used Taylor series to expand fx. Do you want to speak? You have a question?
I don't mean to interrupt, but I just want to ask you a more general question, because the material that you're going through, there is quite a number of disparate strategies that you're teaching us. Okay, so my concern now, I'm trying to think ahead and prep for the final. My concern is, are we going to have to like memorize the base equational forms of each method?
There's nothing to memorize. Everything is open book. I mean, you can use whatever you want.
Oh,
because there's nothing to memorize. I mean, it is an open book exam this time because we are doing it from home.
I see.
Yeah.
I'm sorry, it was a stupid question.
No, it's not a stupid question. It's important that you should know that, don't try to prepare, like, probably I should say it. I will repeat it again. And this is not like a regular exam. You do it from home. So whatever is in front of you, you can use. I will make the exam such a way that you won't find the questions in the internet or something. So I'm really not concerned. You can use whatever you want to use. Okay, so it is formally it is an open book exam. But the questions will be very similar to homework questions. So how we are making a catch here is the time. I'm only giving you 3 hours, so you need to study and you need to know where to look and all of that. Otherwise, you won't be able to finish it within the time limit. But you won't be able to use the code in the final because probably you are better off using a calculator. But if you can, for example, if I ask a question using, let's say I ask you to find a matrix inverse or a 3 by 3 matrix, I will ask you to write down the steps. Okay, then if you just use a program, that's only going to give you the answers, I guess. So other than that, yeah, if you can use your program for sure. The programs that you wrote, you can use. No, you won't. We talked that already. There won't be. I will make sure that you won't do 10 iteration by hand. Okay. So back to the lecture. So Taylor series of fx. So this is the Taylor series. Taylor series expansion of fx around is important, x. So like x0 you had before, probably in the previous lecture you were doing it around x0. This time it is x. So x plus x, that is the x plus h, is a point. It is a point. It's a point around. I'm going to call it one more time. Around or closer to x. You should know that from Taylor series that if x is very high, the approximation will be very bad. So typical value for h is 0.1. Any small number is good. As you get closer to 0, better. When you move away from 0, as h becomes higher, the error will be higher because for example, if you stop here, the error will be order of h squared. Order of h squared will be, as h becomes higher, the error is also becoming higher. That's the point. So that's a Taylor series expansion. And then all you had to do is solve for f prime x, which is here. F prime x is already in the equation. This is f prime x. You have just solved for it. That's fx plus h minus fx divided by h. So this h in the next to the f prime x, that goes to divide. That is why this h squared by 2 factorial became h by 2 factorial. So that's why the error is order of h, because everything after that, everything below this will contribute to error. That's error because we are only taking fx plus h minus fx over h. Everything that is remaining is error, and that is in the order of h, because h squared is less than h squared, h cubed. So we are just taking the largest of the error term, that is in h. So now we can write this in this nice form, that is f prime x is, instead of xi, instead of x plus h, we are calling it I plus 1. X, we are calling it I. No, we are just putting numbers because that's easy. Sorry, x is I. x is I. So then that can be written as fi plus 1 minus fi divided by h. And the important thing is the error is in the order of h squared. Why is that? It was just explained above. Uh, so in other words, we can write it as the first, this one was written with the equality because the error is order of h squared. Or you can say f prime x is approximately fi plus 1 minus fi over h. This is a review so far because of lecture 4. All of these was discussed in lecture 4. Now, second derivative was not discussed in lecture 4, but it is the same approach. So, what we are going to do, let's write fx plus 2h. I already introduced what is 2h means, x plus h, x plus, if I want, using the same notation, I can call it maybe here. This is I, this is I plus 1. The next x plus 2h will be I plus 2, that is x plus 2h. And then, so this will be I minus 1, and then I minus 2, and so on. So we will use these two notations, interchangeably. So for x plus 2h, the Taylor series expansion will be fx plus 2h, because that is a new h, time f prime x by 2h squared over 2 factor. It is just the Taylor series expansion, except instead of the h, we are replacing it by 2h. And that is second one, equation 5 is a regular Taylor series expansion. And then this is written just for this manipulation shown in next. So when you do this, you will come to an equation like this, and that gives us a way to compute the second derivative. The second derivative comes down to fx plus 2h minus, so if I use the same notation as before, that will be f I plus 2 minus 2 f I plus 1 plus f I divided by h squared. That's the second derivative. And then we call something called a high accuracy. And these are the three new concepts that's introduced in this lecture. Second derivative and the high accuracy definition. After that, you will see this is going to repeat. So how to do the high accuracy definition? So we are starting with fx plus h, again the Taylor series expansion, and then from that we take, that's from before, this equation 10 is very similar to how we did the first derivation, and then, but earlier we dropped this term, but this time what we are going to do, we are going to submit this approximation. So we're going to submit that approximation for the second, because earlier we dropped it, but now we are giving an approximation for that. So the advantage is the error become order of h squared. We know that order of h squared means less. So let with that, now I introduced the high accuracy definition of first derivative. Now, this tells us that we can go on and on. We can derive even higher order accuracy, and we can also derive even higher order. Definitely, we can derive second order, third order, fourth, or second derivative, third derivative, fourth derivative using this approach, and also we can make the accuracy high order even higher. So this figure is from the book This table is from the book, figure 2. So summarizes the results. First derivative, second derivative. Let's not go to fourth and third and fourth, but look, this is a very well-known formula, fxi plus 1 minus fxi over h. Look at the error. Error is order of h. And the second, this is a higher order method. We just derived it here, here, here. So why it is higher order? Why it is higher order? Look at the error. Error is order of h squared. That is why it is higher order. Same for second derivative. We just derived this using Taylor series. The error was order of h, but for the higher accuracy. So this is the higher accuracy. Higher accuracy version, the error was order of h squared. Similarly, here's the formula for third derivative, higher order definition. So this is, sorry, I keep confusing the words. This is higher accuracy form. This is higher accuracy. Why high accuracy? Based on all our definition, is the error is order of h squared. Then, as I said, we can keep on deriving formulas for even higher order. So I am talking about two higher things. One is a higher order. That means first order, second order, third order for the higher order derivative. And then I'm talking about high accuracy. That means, if we substitute for higher order terms like I did before, we can make the error term order of h cubed. As you can imagine, we can make the order of h cubed. The catch though is that we will need more data. If you look at this higher accuracy form, here we needed more data, 3 data points, xi plus 2, I plus 1, and xi. Whereas for the first form here, we only needed 2 data points. So it also makes sense if we get more data points, we can make the computation even more accurate. So that is intuitively correct. And the Newton formula tells us a way to do exactly how. So you can compute the second derivative. You can, if you want, a very high accuracy form. So if you just look at the second derivative here, so to compute the basic second derivative, you need 3 data points. If you want to make the accuracy higher, by one step, you need 4 data points. Obviously, if you want it even higher, you will need 5 data points and so on. So this table is just given, as for example, like one sample question here is, I can give some data points and ask you, okay, compute the third derivative such that the error is order of h squared. Then you have to just know which formula to use. All right, so that's for the first forward difference method. So we just finished the forward difference method. Backward and centered are very similar, but can this be we discussed in lecture 4 too, the difference between forward, I mean in terms of error forward and backward, they are the same theoretical error, but center is better than forward and backward. The only difference is that it needs one more data point always for each associated term. You will need one more data point. Again, it makes sense. If you have more data point, the accuracy will be better. So there's not really any surprises there. So I'm going to quickly, so not much formulas or derivations. I'm going to quickly summarize what is backward difference method. So as you know from lecture 4, we will start backward difference derivation by writing a Taylor series around x again, but this time we will write for x minus h. For forward, we wrote it for x plus h. Why is the data we only have previous data? So that's why if we only had previous data, I mean the practical scenario, practical application is you have some data points. You have some data points, and then you want to find the derivative using those at this point. At this point, this is where you need the derivative, but you only have data point before, then you will use the backward difference approach. So where you will use these approaches depends on what situation you are in. So fx minus h, so like before, we will just take f prime x, I write the expression for x prime x. So when the h goes to divide there become order of x, very similar to forward. So that summary of backward difference derivative is fi minus 1 over h, which I also derived graphically using that. So that also makes sense graphically, and Taylor series, they may both make sense. But I cannot derive graphically using second derivative. Probably you can try. All you have to do is take 2 points and find the derivative, and yes, you can derive it graphically also for the second derivative. So without proof, the second derivative formula is given here, and then also higher order approximations are given without showing the steps. So let's go to table 3, backward finite difference approach to differentiation. So you will see the familiar formula first with the error order of h here. That is a high accuracy form for the first derivative, and the formula for second derivative, high accuracy form for the second derivative, and then third derivative, high accuracy form for third derivative, and all the formulas for backward difference approach is given here. So that's the summary of backward difference approach. That's not in terms of error. There's not much. It is only like a convenient based on data point. You just decide when to use. Other than that, you will see the number of data points and the order of accuracy. They all very similar. So with that out of the way, so that's the second approach is backward difference method. The third one is center difference method. So to derive, we will write the formula again, Taylor series formula for x plus h and x minus h. We will write both of them, and then we will subtract one from the other. And then when you subtract and you take f prime x out, which is here, if you bring that to the left side, then you get a formula for the first derivative using centered difference approach. Here, the formula is fx plus h minus fx minus h over 2x. Important thing here is this order of h squared, even though we did not use fx. So technically, we only use 2 data points. So that's, you use 2 data points, but the error is order of h squared. So if you just go back to the corresponding table for centered difference approach. So that's the first formula. Look, the error, unlike before, earlier the error was order of h, now it's order of h squared. So that's better. The centered difference approach is definitely better. If we had the opportunity, we should use that. And that's a higher order form. Look, we only used 4 data points, but the error is now order of h squared, much better compared to here. The high accuracy was just order of h squared, 3 data points. So here it's order of h squared. So that's, you see here that if there's an opportunity for applying centered difference approach, that's the best approach for in terms of error. So that's then all the higher second derivative third derivative and fourth derivative are derived. You don't need to know how to derive. I'm not going to definitely ask you to derive, but what you can do is just take a look and understand. Okay, this is what it is. If you have to use it, you know how to use it. That's all. So that's what we are going to do next. We are going to do an example. Uh, Before we go for an example, so I will come back to this unevenly sampled data, elevate data. That's not that's very similar to what we did during integration. So I will come back to that, but let's do an example here. So you are given a function. The function fx is 4 minus 0.1x to the power 4 minus 0.15x cubed minus 0.5x squared minus 0.25x plus 1.2. So find derivative at x is equal to 0.5 and use h is equal to 0.25. Okay. Okay, so okay, let's see what's done here. So here, obviously this is a toy example, which means we know the derivative, but we are going to pretend that we don't know, and then we are going to use these formulas to compute the derivative so that we can compute the true error, because that's where compute epsilon t, the true relative error, which normally you wouldn't be able to compute for examples. We have the true function is not known. So this is a toy example. True function is known. True derivative can be computed. So we will just compute the true relative error. So here we are just applying the forward difference formula, f x plus h minus f x divided by h. So when you apply, you get a value for the differentiation method is minus 0.1.155, whereas true value is this. So using that, you can compute the percentage relative error. From this point, I'm going to just call it error. But you get the idea. It is actually true percentage relative error. That's what we are computing here. Again, backward formula. So f x minus h is that right? Should this be a, let's go back and look at the formula. So backward formula, it should be fx minus. So I hope this is definitely wrong. Probably this comes from the book, so probably when I wrote I made this mistake, whereas the answer should be correct. I don't know if I will check this. I will note this down for checking, but I'm pretty sure that's the case here. The answer is correct, but I made a mistake when writing this. I'm confident about the answer because this example comes from the textbook. But I check it. Just check to make sure that if that's the case here. Center different method. So that is f x plus h minus f x minus h divided by 2 times h. Just substitute the numbers. So what we should observe here is this. What we should observe here is look at the errors. Forward, backward, center. So forward method, the error was 20 something, backward 26.5, backward 21.7, whereas center is error is 2. So that's, I can say that this error is order of h, then only order of h squared. So you can never predict, you can never compute what the exact error is, but you can tell this error is in the order of h. So whereas order of 0.25, right? Order of 0.25, and then this is order of what is 0.25 squared. order of 0.25. What is order of 0.25 squared? Let me compute that. 0.25 squared, 0.0625. So that's in the order of 0.60625. So order of 0.25 multiplied by something, obviously. Order of 0.25 multiplied by something. And then the other one is order of 0.0625 multiplied by something. So that's, you can see also the error dropping so much when you use center different approach. Now look, so this is a high accuracy form. So we are just applying the high accuracy method. So for forward, you get 5% error. Backward, you get 5% error. And look at the center, 0. Now, once again, it's a toy example, but the centered, I don't know if it is 0 point something or it is just completely 0. But that shows the power of this centered approach as really fast. Okay, so that's an example. So I just did an example using these 3 different approaches. We only did the both forward, backward, and centered, and the high accuracy versions of each of these 3. But we didn't do second derivative. Okay, now the last thing. So we just let me go back to. So we studied about forward method. We studied about method, and we studied about central method, and we also did an example for these 3 methods. What is remaining now is unevenly sampled data. If you see this derivatives everywhere, it all assumes that the data sampled evenly. So when the data is not sampled evenly, this formula cannot be applied. So what should we do? So there's a small discussion about what to do in that. So when you have unevenly sampled data, for Taylor series, the data should be evenly sampled. So if you are in a situation where we don't have evenly sampled data, we can use Lagrange method. So if you just go back and look at the Lagrange polynomial, you can write a second order, you can approximate a function. If you have 3 data points, you can write this function as using an interpolation, Lagrange interpolation. You will see that's writing that function. You have 3 data points, you can write fx as a0 plus a1x plus a2 x squared and find those 3 coefficients a0, a1, and a2. Instead of to find those 3 coefficients, you'd be solving a 3 by 3 linear system of equations. Instead, the Lagrange method gives a closed form formula. If you just write this function in this way, you don't need to compute the formulas. It is a big computational saving. That's what it is. So see, everything is known here. X1, X2, X3 is known. Y1 is fx1, y2 is fx2, fx1, this is fx2, this is fx3, all known. So the formula is available. Then all you have to do is take a derivative. Just take a first derivative, and that is again a closed form formula. Just so that's it. That's it. If you don't have, so definitely we are going to have errors associated with it. That was not discussed in this lecture, but let's see if the examples tells us something. No, the example is a different example. What would have been nice is if you use the same example as before using Lagrange method. That will give us tell us comparison of errors. But in this example, I'm just considering a different. Maybe that's something for a homework. So it is 3 data points are given. So actually 4, 0.6, 0.7, 0.8, and 0.9. So that's again evenly spaced. Okay, that's a good example. Find the derivative of x was assuming the knowledge of the 3 data points. Okay, assuming the knowledge of 3 data points. So we are going to do this, assuming the knowledge of 3 data points. So if you select 0.7, 0.8, okay, that's 0.8. You see the data is not evenly spaced. If I select 0.7, 8, and 9, they are actually evenly spaced. So we can, what you can do is you can apply the Newton method and see that the errors comparison. But in the second one, selecting 0.6, 0.7, and 0.9, that is not evenly spaced. So, but there's not much to say here. What would be nice is, select these 3 points and then do the Newtons. Well, you cannot compare this to the you cannot compare this to the equally spaced approach, right? Right. Yeah. Okay. Anyway, that's I'll think about maybe a question for you to. Again, there's not much here. It's well, if the data is evenly spaced, the Newton's approach, sorry, the Taylor series approach that we studied in these three can be used. These three approaches can be used if the data is equally spaced. So we just talked about this method for unevenly spaced data. So we use Lagrange method. The problem with this example, I don't like this example, probably it comes from the textbooks anyway, is that the data is once again evenly spaced, but we are doing it in 2 different ways. In the example 1, we are using 0.7, 0.8, and 0.9. That is again evenly spaced. So what would be nice is to use, that's definitely a, something I will do, that we can compare this first derivative. So we are just computing the derivative at 0.8. So, okay, here's a question. So we have 3 data points, 0.6, f 0.6, and then 0.7, f 0.7, and then 0.8, f 0.8. Let's say we are going to use, out of the 3 approaches, let's say we want to find f prime at 0.8. Now, what approaches that we studied so far will be useful? Can I use forward difference approach? No. Yes. Can I use backward difference approach? Yes. Yes. No. Can I use center? No. If I want to use center different approach, because remember, I want to find f prime at 0.8, I will need data at 0.9, which I don't have. I'm assuming I don't have this data. Yes, if I assume that data, I can also go center different approach. Yes. But if I only have these 3 data points, and then I want to compute the derivative at 0.8, then I'm only allowed to use the backward different approach. Others cannot be used. Yeah, don't worry about the question. Of course, I will give all the details about the questions if I'm asking questions. But the important thing, at least at the lecture, is to understand this. Okay, so that's it. As I said, this is a pretty short and pretty straightforward lecture about numerical approaches for differentiation. Any questions? That's all for the lectures. Yeah, there's one question. I might add one more question here for the homework, and then I will assign the homeworks. I don't know if you want, I mean, I can tell you already that, these latter part of the lectures is differentiation. I mean, the next two lectures, ordinary differential equation and partial differential equation, these are all part of the program that you will need to know. And then, but unfortunately, it won't show up. This question won't show up in your lab. But I just wanted to emphasize that, you can write an algorithm for numerical differentiation as well, and you can write a C++ program as well. So yeah, I'm going to just mention that, and we can try that, but there won't be a lab or the programming questions for you to do this. But I will encourage you to do, for example, for homework questions, you can write them if you wanted to. At this point, you should be pretty comfortable with the C++ and any algorithm like this one. You should be able to program. So I'm sure you can. So that's why I'm just only focusing on the approach. That we did this many times. You will study about a new approach and you will go and program it. So it's a kind of a same drill now, especially for the remaining two lectures. All right, any questions? All right, so if there are no questions, I want to just emphasize that this lab, project one is available. It is due on December 1st. If you want some extra time, I think it is possible. But you already have 2 weeks to complete this. The important thing is please work on Replit so that we can see the progress rather than you work on somewhere else and paste your code. We don't really know where that code came from. That's a big problem. So we don't have a feature to solve this problem. That's why I asked that you please work on Replit so that we can see that you have been working. It will tell you when you worked on. All of those can be seen. So that gives us confident that it's your work. Thus, we are almost, 2 more lectures. So, so this is how the remaining class is going to go. So there are 2 more lectures. One is going to be available as a recording, probably 2, both of them. Then, if I manage to record both of these lectures, and then from next week I will start to do reviews, which means I will just do the homework questions in class. If you want me to touch certain topics, you need to let me know and I will do it. Yes. Any questions? I see a raised hand, Sydney.
Okay, I know I'm beating this dead, but I just want to do my best to prepare for the final. So my strategy that I was going to employ was going to be to go back through all of the homework sets, and where I haven't already written up code snippets to answer the questions, I would go through that and start writing up the code, because I was thinking that would save me time when the final comes around.
Yeah, that's a good way to practice, because end of the day, this course is all about studying new concepts and then programming them.
So I can use my code snippets on the final exam.
Yeah.
Perfect.
The only thing is, you cannot just, well, the question will be clear enough. For example, if I ask you to show the answer at this step, the answer at this step, of course, you can modify your program to give you an answer. That's, it is similar to using a calculator.
I see. Okay. Thank you very much, sir.
No, final, there won't be any question. It is only a 3 hours, right? So I won't, it is, final doesn't require you to, so, no, it's only about, about formulas and, derive this and, show this and compute things like that. You can use it. This is a final is like you can bring a program or calculator. So that is what it is, right? You can program all of these, keep it pre-programmed, that's fine. But then I will ask, okay, show the steps, what get this, and I will change the question in a way that shows your understanding. That's all. I don't know if I will be doing all the questions. That is the plan. We will have 3 or 4 lectures now for us. But let's see. It also depends on the time. So I think when I start, I will have a good idea of. But all the question, homework 1 to homework 11, I will touch them. Some homeworks have many questions, like 6 or 7 questions. In that case, I might just select the difficult one, I believe. But if you want me to do certain questions, let me know and I will take that. The plan is to do all the homework questions. Yes, that's a plan. Yeah, we will start the review on Tuesday. Yeah, there will be some more quizzes. I was just a little busy last week, so I don't know about this Thursday, but definitely we will do it in the next Thursday, because the idea of having more quizzes, I can give you that bonus quiz. We still cannot, because we only had 2 quizzes. If I do 2 more quizzes, then 1 will be bonus. So don't think it as a bad news. It is actually good news that having 2 more quizzes, you will get an opportunity to drop that lowest quiz. Yeah, that's I want to give you a bonus quiz as well. So let's we have at least 2 or 3 more weeks. I don't know. Let's see how many weeks we have. November 17th today. We have this week, next week. We have 1 more week, and then December 9th is the final day. So we cannot technically we have 4 more weeks. So we can definitely have 2 more quizzes. Final. It is cumulative. Final is cumulative. How many questions? It is 6 hours. Usually half an hour per question. So you can expect 6 questions. No, sorry, it's not 6 hours, 3 hours. 3 hours, 6 questions. All right, any other questions? Let me see, how many homework did I upload? So you have homework 9, so 2 more homeworks. Yep, we need to mark them. And then lab is done. You have project. Now we're almost there. All right, everyone. There are no questions. We will meet live on Tuesday, but I plan to upload those remaining lecture videos before that, so that we can start with the review on Tuesday. Have a good day, everyone. Stop the